What if I told you that even the best machine learning models is only as good as the data it is trained on? You see, raw data is often messy, incomplete, and unstructured. Without proper transformation, even the most advanced AI models will struggle to make accurate predictions. This is where feature engineering comes in. Greetings, everyone. I am Anupam Singh. It is a pleasure to have you all here. I warmly welcome you to this presentation on feature engineering, where we'll delve into its concepts, techniques, and applications. In this video, we are going to break down in feature engineering, one of the most critical steps in building robust machine learning models. We'll cover different types of missing values and how to handle them effectively, resampling techniques to deal with imbalanced datasets, encoding methods to convert categorical data into a machine-readable format. If you're into machine learning, data analytics, data science, or AI, this is a must-known concept. So grab your notes and let's dive deep into feature engineering. Missing values are a common challenge when working with real-world datasets. They can occur for many reasons: data collection issues, human errors, or even intentional omissions. Before we can fix them, we need to understand why they occur. Missing completely at random. There is no specific reason why the data is missing. It happens randomly. For example, a weather sensor fails randomly due to power outage, leading to missing temperature readings. Since there is no pattern, we can impute the missing values using mean, median, or mode method. Missing at random. In this situation, missing values depend on other observed data, but not on the missing value itself. For example, in a job survey, younger participants might be more likely to skip the salary field, but their actual salary isn't causing the missing data. To deal with this issue, you can use regression models like k-nearest neighbors or decision trees to predict and fill in missing values. Missing not at random. Here, the missing values are directly related to the missing data itself. For example, people with high incomes might purposely leave the income field blank in surveys because they don't want to disclose their earnings. The best approach is to analyze the root cause and decide whether to remove the feature entirely, create a new category, for example, not disclosed, or predict the missing values. Now that we know why data goes missing, let's explore some common techniques to handle it. Mean, median, and mode imputation. It is simple and effective, suitable when missing values are small. For example, if 5% of a dataset is missing ages, filling it with median age works well. Forward and backward filling. It is commonly used in time series data. For example, if stock prices are missing for a day, we can use the previous day's price to fill the gap, that is forward filling. Predictive imputation. It uses machine learning to predict missing values. For example, if customer spending behavior is missing, we can predict it using age, income, and past purchase history. If a feature has more than 40 to 50% value, it might be best to remove it altogether. This technique is known as removing rows and columns. Sometimes you have to discuss with the product owner to decide the threshold value to remove for removing rows or columns. Choosing the right method depends on the dataset and the business problem. In machine learning, we often deal with imbalanced datasets, where one class is significantly more frequent than other. Now, why is this a problem? Let us understand with an example. If 95% of transactions are legitimate and only 5% are fraudulent, a model could simply predict legitimate every time and still be 95% accurate, but it would fail at detecting frauds. To fix this, we use resampling techniques to balance the dataset. Resampling methods are techniques used to adjust the distribution or sample size of data, often applied in situations involving imbalanced datasets or statistical validation. Some common resampling methods include upsampling. This technique increases the minority class by duplicating existing samples. For example, if we have only 500 fraudulent transactions and 10,000 legitimate ones, we can duplicate fraud cases to balance the dataset. Downsampling technique. This technique reduces the majority class by randomly removing samples. For example, if 10,000 legitimate transactions exist, but only 500 fraudulent cases, we reduce the majority class to match the minority classes. SMOD, that is synthetic minority oversampling technique. Instead of copying data, SMOD creates new synthetic samples based on existing ones. Example, If female users are underrepresented in a recommendation system, Smooth generates synthetic female profiles based on existing user data. Resampling ensures that a machine learning model doesn't develop biases towards the majority class. Machine learning models work with numerical data, not text. To process categories like red, green, and blue, we need to convert them into a numerical format using appropriate encoding techniques. This transformation enables the model to analyze the data effectively and derive meaningful insights, ensuring accurate and reliable predictions. One-hot encoding. It is used when categories have no order. Each category is represented as separate binary column. In each column, whenever a particular instance occurs, it is represented as 1, while all others are marked as 0. It is best for categories with small and fixed values. Example, car brands or cities. Label encoding, also known as ordinal encoding. It is applied to categories with a meaningful order or ranking, where the sequence reflects the relative importance or level of categories. For example, categories like education levels can be encoded numerically, where high school can be encoded as 0, bachelor's as 1, master's as 2, and PhD as 3. It is best for ordinal data, that is, where order matters. Target guided ordinal encoding. This technique assigns numeric values to categories based on their correlation or relationship with target variable. It is particularly useful for encoding categorical variables in a way that enhances the predictive power in a supervised learning model. For example, in a credit risk model, loan applicants from different cities may have different default rates. Cities with higher default rates get lower ranks. Choosing the right encoding method is crucial. Wrong encoding can mislead the model and affect performance. Let us explore some of the key best practices for encoding data. Use one-hot encoding for unordered categories like colors, city names, as it ensures each category is treated independently without implying any hierarchy. Use label encoding for ordered categories, as education levels, product ratings, as it preserves the inherent ranking among categories. Avoid label encoding for unordered categories, as it introduces misleading numerical relationships that may negatively affect the model's performance. Handle high cardinality. For categories, categorical features with many techniques, very unique values, that is thousands of cities, consider techniques like target encoding or embedded methods to prevent feature explosion with one-hot encoding. Scale numerical labels for encoded ordinal data, considering normalization or scaling to improve model performance and avoid biased feature weighting. Consider model typing. Understand your algorithm's requirements. For instance, tree-based models like decision trees and random forests often handle encoded data more effectively than linear models. Track correlation with target. Use techniques like target encoding to create meaningful numeric mappings based on relationship with the target variable, but ensure proper validation to avoid overfitting. Regular validation. Perform cross-validation to assess the impact of encoding strategies on model performance and prevent overfitting. Feature engineering is an art and science that transforms raw data into powerful predictive features. Whether it's handling missing values, balancing datasets, or encoding categorical variables, mastering these techniques will help you build better and more accurate machine learning models. Try applying these techniques in real-world datasets using Kaggle competitions are a great start. Follow me on LinkedIn and YouTube for more practical insights. If you found this video valuable, hit the like button and subscribe for more content. Thank you.